Okay, we're on 5.3, the ionization of water. We're skipping the warm-up and we're going straight to the ion product constant of water. You learned in a previous section that water can act as an acid or a base, right? It's amphiprotic, so it can accept a hydrogen ion or donate a hydrogen ion. So if I have two neighboring water molecules next to each other, one of those water molecules can give away a hydrogen to the other, and you would form a hydronium ion and a hydroxide ion. Now we can get an equilibrium between water molecules, and since we can get an equilibrium, guess what that means? We get another equilibrium constant. Okay, so far we have KEQ, KSP, KA, KB, and now I will have KW. So when it is just water, and we're at equilibrium, I replace the EQ with a W, and I would call this the water ionization constant or the ion product constant. So if you were writing the KW expression, you would have the concentration of hydronium ions times the concentration of hydroxide ions, but you're allowed to eliminate these two water molecules because they are liquids and those are not included in your expression, okay? When you're at 25 degrees Celsius, your KW has a defined value. Its value is 1 times 10 to the negative 14. This is extremely helpful because that means if you have one of these concentrations, you can calculate the other one. So that's what we're going to do in a little bit. Let's turn the page. You know that water is neutral, right? So since water is neutral, and if you're at 25 degrees Celsius, then we can use 1 times 10 to the negative 4th to calculate the concentrations of hydronium ions and hydroxide ions in solution. And they will be the same. So if I can take the hydronium ion and hydroxide ion and substitute an x for each one, which would give me x squared equals 1 times 10 to the negative 14th, take the square root of both sides, you're going to get the hydronium ion and hydroxide ion concentration would be 1 times 10 to the negative 7. Okay? Now, if you take a look at the quick check, the auto-ionization of water is endothermic. And if the temperature of water is increased, what do you think is going to happen to the concentration of hydronium and hydroxide ions? Well, in the past, when we increased the temperature, which direction did we shift, left or right, generally speaking, for endothermic processes? You're right, shift right. If I add heat to an endothermic process, I'm going to consume that, I'm going to shift right, I'm going to produce more product, which means in this case, I'm going to increase the concentration of hydronium ions and hydroxide ions. Okay, so that means my KW should also increase because KW is equal to the hydronium ion concentration times the hydroxide ion concentration. So if this goes up, the KW goes up. So therefore, 3 dots means therefore KW increases. Take a look at number 2. At higher temperatures, how will the concentration of hydronium ion and hydroxide ion compare to each other? They will actually be the same. They will equal each other. Okay. Number 3, I'm at 10 degrees Celsius. My KW is 2.9 times 10 to the negative 15th. They want us to calculate the hydronium and hydroxide ion concentrations of water at this specific temperature. So you know that the KW equals the hydronium ion concentration times the hydroxide ion concentration. So if I put this KW value here, that would be 2.9 times 10 to the negative 15th equals these concentrations. I can use a variable for hydronium and hydroxide. Let's just substitute an x for each one, which would end up giving me x squared. And then if I want to solve for x, what would I do? Square root. So take the square root of both sides, and you'll end up getting 5.39. Yeah, 5.4 times 10 to the negative 8 molarity, which would be the concentration of each ion. Okay? to adding acid or base to water. You know that water is neutral, has a pH of 7, but if I add an acid to it, won't I produce hydronium ions? So if I produce hydronium ions, my hydroxide ion concentration comes down. And then if I add a base, I produce hydroxide ions, and my hydronium ion concentration goes down. So if we increase the hydronium ion concentration, it causes a decrease in hydroxide ions and vice versa. The hydronium ion concentration is inversely related to the hydroxide ion concentration. So one goes up, hydronium ions go up, hydroxide ions go down. Now, here we have a summary, these 3 bullet points down here for acidic, neutral, and basic solutions. If you are acidic, your hydronium ion concentration will be greater than the hydroxide ion concentration. If you're neutral, those will equal each other. If you're basic, the hydroxide ion concentration will be bigger than the hydronium ion concentration. So far, sort of common sense. Agreed? Okay, so let's go on to here, the practice problems. Calculate the hydronium and hydroxide ion concentrations in 0.15 molar HClO4. We're assuming our temperature is 25 degrees Celsius, and they want us to justify that the solution is acidic. So if they give you the concentration of an acid, then you know acids ionize. They will form hydrogen ions in solution. So the original concentration of the solution should be the concentration of the hydrogen ions. Agreed? Aren't hydrogen ions the same thing as hydronium ions? Yeah, because hydrogen ions immediately combine with water to give you this. So this hydrogen ion concentration that we have written here is the same thing as the hydronium ion concentration. So I'm halfway done with my problem, right? Because now we have this done. Now I need the hydroxide. Well, if you're at 25, you know that Kw is 1 times 10 to the negative 14. And your hydronium ion concentration is 0.15, and I can calculate the hydroxide ion concentration using this Kw value. So if I divide by 0.15 on each side, my hydroxide ion concentration will be 6.7 times 10 to the negative 14. Okay? Is it that bad? No. And if I had to justify that this solution was acidic, you want to look at the concentrations and just compare them. Your hydrogen or hydronium ion should be higher than the other one. And it is. 0.15 molarity is a lot bigger than 6.7 times 10 to the negative 14. So that's telling you that your hydronium ion concentration is bigger than your hydroxide ion concentration, which means this is definitely an acid. Does that make sense? Okay. I'm going to do one more. And then that's it. Number 2, calculate the hydronium and hydroxide ion concentration in a saturated solution of magnesium hydroxide. We talked about saturated solutions back when we talked about KSPs. You should have earmarked that page because since we're using magnesium hydroxide, which will produce a magnesium ion and 2 hydroxide ions, if you turn back to the page that has the KSP values on it, you can look up the KSP for magnesium hydroxide, which is 5.6 times 10 to the negative 12. Okay, have you so far? Now, if I use this value to calculate the hydroxide ion concentration, wouldn't I set this up where I've got the magnesium ion concentration times the hydroxide ion concentration, and since there's a coefficient of 2, I'll have a squared on the hydroxide, right? I need to use variables for these ions in my equation, so I'm going to use an x for magnesium, and I'm going to use a 2x for hydroxide. So this is going to be 5.6 times 10 to the negative 12 equals x for magnesium times 2x for hydroxide, and you can't forget the squared that you had there. Yeah?
So the coefficient goes down like in front of an x, so that's what's going to be.
Yes. 2x squared is 4x squared, agreed? 4x squared times x is 4x cubed. What should I do now?
Divide by 5.6 times 10 to the negative 12 by 4.
Yeah, divide by 4 and then cubed root it. So you would take both sides, you could say to the 1/3 power. That just is kind of easier for me to write, considering how much room I have. Okay? You're going to end up getting an x value of 1.1 times 10 to the negative 4th. Okay? Now, my hydroxide ion concentration was 2 times x. So the hydroxide ion concentration is 2x, which is 2 times 1.1 times 10 to the negative 4th, which is 2.2 times 10 to the negative 4th.
Was it also cubed? I mean,
I already did that.
squared?
No.
Oh, okay.
Now, from there, I'm at 25 degrees because it said so up above. So now I can use my Kw value of 1 times 10 to the negative 14 equals the hydronium ion concentration times the hydroxide ion concentration, which is 2.2 times 10 to the negative 4th. Divide both sides by 2.2 times 10 to the negative 4th. And you're going to get a hydronium ion concentration of 4.5 times 10 to the negative 11. And you're done. Okay? Different application of KSP. We're not going to do number 3. Understand me?
Mm-hmm.
Questions? We're skipping mixing solutions of strong acids and bases. Your homework is review questions 5.3 numbers 2 and 4.